Hello everyone, my name is Maggie Chen and my paper is on a comparison of K-means and convolutional neural network algorithm for skin lesion imaging. I was mentored by Dr. Perung Liu. So a little bit more about the background and the problem of the paper. Depending on the case and disease, percentages for inaccurate diagnoses in the medical field may range from 25% to as high as 70%. And ever since these errors were discovered, the percentages have remained around the same. These errors can be attributed to differences in education or something as simple as human bias, which we all have. However, a well-trained computer algorithm can minimize these factors. A study compiled various deep learning methods and analyzed its effects in 6 fields of medicine. They discovered processing challenges in the 3D radiology images, but, however, they still found that the algorithms were more effective than humans. In a study in 2021, they analyzed techniques for cancer diagnosis and found CNNs provided the highest accuracy and offered advantages in recognizing complex patterns of cancerous tissue. In our study, we chose to focus on skin cancer as skin cancer is the most common form of cancer in the United States and is most treatable when detected early. A rule to commonly detect melanoma, which is skin cancer, is the ABCDE rule. B stands for borders. If you notice irregular borders, that is an indicator of possible cancer. We can see in figure 1, which are the images on the right, some examples of skin lesions with irregular borders. So the two algorithms we decided to test and compare with each other is the K-means algorithm and the CNN. The K-means algorithm is an unsupervised machine learning technique that separates data into clusters or groups. They assign centroids to random values in the data and then groups each data point to the centroid that is closest in value. Initially, this grouping is very inaccurate as the centroids are randomized. However, it then calculates the mean value of all of the data points in each cluster, and that mean value is set as the new centroid value. This process repeats over and over again until the centroid values stabilize or a predefined maximum number of iterations is reached. You can refer to the figure on the right for a more visual representation of how a K-means algorithm works. In our study, we chose to train the K-means algorithm with 2 centroids and a varying number of maximum iterations, which will be set at 1, 2, 3, 4, and 9. We will also record the dice score and store the prediction images to allow for visual comparison of the results. The second algorithm is the CNN, or the convolutional neural network. This is a supervised machine learning algorithm, meaning training requires a set of labeled data. This is modeled off of the brain, in which an interconnected system of neurons work together to build complex images from the simpler patterns. Now, usually, a dataset typically goes through a series of pre-processing steps, but in our study, we only chose to randomly crop the images. Sometimes you may also see some dilations or rotations to create an even larger data set. A CNN is made up of several layers, which can range depending on the purpose of the study. The convolutional layer is always the core. Kernels, which can be described as filters, slide over portions of the input data. In our study, the input data is the pixels of the images of the skin lesions. The training data will be reintroduced throughout the algorithm for a specified number of epochs, which is similar to repetitions. Not enough epochs do not give the model enough time to fully learn the patterns in the data. However, more epochs do lead to longer training time, but may result in more accurate algorithms. However, too many epochs can lead to overfitting and inaccurate results when shown new images. At the end of the finished model, a separate data set with new images will be used to test and determine the accuracy of the algorithm. In our study, the CNN will be trained with 3 layers and a varying number of epochs, which will be set at 1, 2, 3, 4, and 9. The dice score will be stored, and the prediction images will also be stored for visual inspection. You can refer to the model on the right to see a visual representation of a CNN. So a little bit more about the dice score. In this study, the dice score was used to measure how well the k-means algorithm performed, which is a common way to evaluate the overlap between predicted clusters and the actual data. The dice score ranges from 0 to 1, where 1 means perfect overlap and 0 means no overlap at all. A higher dice score indicates better results, as it shows that the predictions are more similar to the true images. We also chose to use the CNN and perform the dice score on the CNN as well, as that is similar in being able to show the prediction image and the true image differences. So a little bit about our results. Here in the table above, you can see how when we increase the maximum iteration, the runtime increased slightly, while the dice score also increased, and we can see the accuracy score remained approximately the same. I plotted the results of our table into a graph where we can see a somewhat linear trend from 4 maximum iterations and on. And finally, I included an image to show a visual representation of a dice score. So the white border is the difference between the ground truth image and the predicted image that the k-means predicted. In this case, you can see the small border is rather small, and therefore this would be a rather accurate result. Here is the results of our CNN network. Similarly, we have number of epochs down on the left, and then the training time does get significantly longer as compared to the k-means, while the dice score increases pretty linearly as well. And we can see that on the graph shown below. As the maximum number of iterations increased, the dice score improved, starting from at 0.1 to as high as 0.942. However, in our k-means, we saw dice scores more similar to 0.942. And so this suggests that allowing the algorithm to run longer gives it more time to refine the clusters, leading to better alignment with the actual data. The algorithm achieved more accurate results, which can be reflected by the higher dice scores. This method, as in the k-means capacity to cluster data without prior labels, offers a distinct advantage in scenarios where labeled datasets are time-consuming to create. However, it does have its disadvantages as its reliance on centroids and the risk of inaccurate clustering due to the dependence on initial randomized assignments highlight the importance of careful calibration. And we can see that in our study when we saw only a slight increase in runtime and a very good dice score, typically pretty much all around. And our high was 0.942, but that number was not reached when the maximum iterations was reached. Rather, it occurred with a maximum iteration of 2. And this kind of proves how the algorithm's performance is dependent on its initialized values, which are random, and that can lead to inconsistent results, which we saw in our study. In the CNN, the training data combined with the layered structures of CNNs enables these networks to achieve high accuracy in identifying the complex borders of skin lesions. As we saw in the graph, the results showed a linear increase in runtime, and the dice score also increased consistently as the epoch number was increased. However, what is surprising is that the dice score never reached as high as when compared to the k-means results. And this can be explained possibly to the slower processing computing speeds of the resources available to us. And therefore, we were not able to test higher variables such as 15 or even 20. And this lack of data may contribute to the lack of the bigger picture of the CNN's capability. So overall, the CNN's results were worse compared to k-means, but this may be due to inadequate computing resources. But the difference is we can see that the dice scores were low at the start for CNN, but consistently increased. And that suggests that the CNN may eventually surpass that of the k-means, as the k-means was relatively stable. This highlights how important it is to give the CNN enough training time, because while it may start off with lower accuracy, it is designed to ultimately outperform simpler methods like k-means when properly trained. So here is the conclusion taken directly from my paper. In conclusion, the integration of computer vision and machine learning into the medical field represents a significant advantage in reducing errors associated with the interpretation of medical images. The unavoidable variability in human analysis, influenced by factors such as education, cognitive differences, and biases, has contributed to many inconsistencies in diagnosis throughout medical history. By developing computer vision and advanced algorithms like k-means clustering and convolutional neural networks, the potential to improve the accuracy of medical image interpretation is unbounded. The comparative study of k-means and CNNs in detecting skin lesions, a critical task in dermatology, represents the strength and limitations of each approach. And finally, here are the sources that I used in my paper.